Hello everyone, this is FOCS 23's talk, Sub-quadratic 1 plus epsilon approximate Euclidean Spanners. My name is Hengjie Zhang, and this work is with my advisor, Alex Andoni. Let's first introduce the notion of spanner. Say, given a graph G, and we construct a new graph H such that we take all the points from G, and we take a subset of edges from G. Suppose for every pair of points ST such that the distance ST in H is bounded by 1 to alpha times the distance ST in G, then we say the H is a spanner of stretch alpha for G. And a classic result shows that there is a trade-off between alpha and the size of spanner. For integer k larger than 1, when the stretch is 2k minus 1, the size is n to the 1 plus 1k. And if we minimize the stretch for sub-quadratic spanner, the best we can get is alpha equals to 3 with n to the 1.5 edges. And this trade-off is tight on the Erdos-Gerst conjecture. And the Euclidean spanner is a special one. Suppose we are given n points in Euclidean space Rd. There is a hidden complete graph G that we take these points as its vertices, and for every pair of points, the length of the edge is literally their Euclidean distance. And the definition of Euclidean spanner is exactly the same as the definition of a generic spanner. So here we have a small example. H taking 2 edges from G, and it has a stretch √2. So there is a rich list of literature studying the low-dimensional case, where D is a constant. The best bound for alpha equal to 1 plus epsilon is the size is n times epsilon to the minus d plus 1. However, little is known for the high-dimensional case, and the only result we are aware of is by HIS 13, 10 years ago. And the trade-off is that for any k larger than 1, we can get a stretch roughly equal to 3.4, which is root 12 exactly. Root 12 times k with a size equal to n to the 1 plus the k squared. So if we compare to the generic spanner, which we introduced several pages ago, this bound for a small stretch alpha doesn't even beat the generic bound. So a natural question to ask if there exist better spanners for high-dimensional spaces. And particularly, we want alpha to be the stretch to be 1 plus epsilon, and the size is sub-quadratic. And why do we care about the Euclidean spanner? It is because it's a generic approach to speed up tasks. Suppose we're given a bunch of points, and we have a test of a point. Suppose we get a Euclidean spanner from those points, and it's a sparse graph. Then we can do the test on the graph. For the low-dimensional case, early literature suggests that the Euclidean spanner can be used on network design and motion planning, etc. For the high-dimensional case, which is our main focus in this talk, due to the recent rise of machine learning, high-dimensional tasks have become popular because to deal with images, text, and videos, the common thing to do is to first embed those objects into high-dimensional vectors. And if two vectors are close, this suggests that these two images might represent the same thing. A recent paper used the spanner building technique from HRS 13 to build the structures like similarity graph, which is a downstream for multiple tasks like clustering, classification, and graph learning. We also find applications for theoretic application, which is to compute the Earth mover distance between two distributions. The Earth mover distance was introduced from the statistics. And for simplicity, we consider the following simplified problem, where we have two sets P and Q, and we want to calculate a mean cost matching between these two sets. So this way. Classically, this problem can be solved by running a linear programming with n-squared variables, or we can run a mean cost flow, which with the n-squared edges. But neither of them can beat the n-squared bound, since the input is already n-squared. And we hope that the expander, the Euclidean spanner can help in this task. Suppose we have a Euclidean spanner with a low stretch and with sub-quadratic number of edges, then we are able to approximate the EMD distance very well. Actually, we are aware of recent papers considering the hardness of to 1 plus epsilon approximate computing the EMD distance in sub-quadratic time. And our result, together with BR23, we independently prove that EMD distance can be approximated efficiently. However, we are multiplicative approximation, while BR23 is the additive approximation. And before introducing our main theorem, we have to distinguish the Steiner point with we define it as a non-metric Steiner point. It is because in the geometric community, we often refer the Steiner point as the extra point, which is the real points in RD space. Whereas our results show that if we only use a real point in RD space, we cannot even beat the √2 bound. Because let's think about this instance. There are n uniformly random points on a unit sphere, and their pairwise distance will concentrated on √2. Suppose we are only allowed to add points within RD. The best we can do is add a Steiner point as the original point, and then link this point to every other point with distance 1, creating a star. However, this star has a √2 stretch. And if we think cleverly, we can actually set the length of the edges as 1 over √2. But then this point doesn't belong to any point in RD space, which we refer as the non-metric Steiner point. And in this instance, it gives alpha equals 2. Our main results show that if we would allow this non-metric Steiner point, we can actually construct such Euclidean spanner with the 1 plus epsilon stretch and with the sub-quadratic number of edges. We save the epsilon cube from the exponent. And furthermore, if we allow to use directed edges, which we constructed a directed spanner, we can further save extra epsilon on the exponent. Here, the directed spanner has the same property as the undirected spanner, except it can have directed edges. As a corollary, We showed that using the directed spanner, we can already solve the EMB problem using near linear time in-course flow algorithm. And beyond EMB, we showed that for every Wasserstein WP for constant P, we can calculate 1 plus epsilon approximation in sub-quadratic time. To present our result, let's first review the spanner construction from the previous HIS 13. Let's focus on one scale, say R equal to 1. And the goal of our spanner construction is that for any two close points, P and Q, we should have at least one path of length at most alpha in the spanner. Meanwhile, we need to guarantee that no pair PQ is shortcut in the spanner. Specifically, there should be no path of length less than the distance of PQ in the spanner. And they use a locality-sensitive hashing as a basic tool. Remind that the locality-sensitive hashing maps points into many buckets. And if 2 points PQ is close, then the probability they collide in some bucket is high. If 2 points F and Q is far from each other, then the probability they fall into the same bucket is small. We take an example here. Here is 3 points P, Q, and F. And let's focus on the point Q. We execute locality-sensitive hashing, and the points are partitioned into multiple buckets. Suppose in the ideal case that no far points fall into the same bucket, then to construct our spanner, we use the star gadget. Because no far points are in the same bucket, this means every point in this bucket is close to each other. So their distance is at most alpha. So what we can do is to create a star gadget, create extra point for every bucket, and link this point to every point else in this bucket with the distance alpha over 2. In this way, every pair of points are linked by a path of length alpha. And in each iteration, we added only n edges, because every point fall into one bucket and link one edge. To make sure the close point PQ meets in at least one bucket, we need to repeat this procedure at least n to the 1 over alpha squared times. And because each time we add n edges, then hopefully we construct a spanner of n to the 1 plus 1 over alpha squared edges. So for alpha larger than 1, this is a sub-quadratic number of edges. So there are multiple execution of locality-sensitive hashing. However, in some cases, Q will collide with a far point. And if we construct a star gadget, we will create a shortcut that will break our spanning. Because the distance of Q and F is larger than alpha, and we create a path of length alpha. Let's take a closer look at what the real issue is when Q collide with a far point. So typically, the probability a close pair PQ collide is at least n to the minus 1 over alpha squared. And also, for far points by union bound over all far points, which can possibly be n of them, the probability Q collide with some far point F is less than 0.1. And as we can see, the later probability is much larger than the former probability. And these two events are also not independent. So it could be that whenever Q collide with a close point P, Q also collide with a far point F. And because we are not allowed the shortcut happen, so Q can never create a path to P. So for the independence, here's a bad example where Q and P and F lies on a line. Think about alpha equal to 1 plus epsilon for very small epsilon, so that Q and P are close pairs, Q and F are far pairs. However, F and P are really close. So as we can see, these two events that P and Q collide with the event Q collide with F is highly correlated. And the method of HRS 13 is to make the far collision extremely unlikely. So we boost the probability 3 times so that the close point collide with probability n to the minus 3 over alpha squared. While the far point collide is extremely small, which we can union bound on all pairs of F and Q to ensure that no such pair, no far pair collide. So in order to have close point P and Q collide with probability at least 1 over n, alpha should at least be larger than √3. So here is a reason why HRS cannot achieve 1 plus epsilon approximation, because they lost √3 factor here. So how do we get around of this problem? Let's take a look at the directed spanner, which is simple. We split the data point into two sets, P and Q. We will guarantee that we only add passes from Q, the set Q to P, and not adding passes from Q to Q or P to P. And our spanner will only guarantee that for every Q prime from Q, P prime from P, Q prime and Q prime and P prime, if they are close, they will be connected by a path of length alpha. And also, the locality-sensitive hashing has an alternative view, which is the data structure view. Say the green points are points from set P, and the blue points are points from set Q. So the data structure has a pre-processing phase and a query phase. In the pre-processing phase, we process for every P prime in P, and we put P prime into many buckets. So in the standard LSH, we only put 1 point into 1 bucket, and we repeat multiple times. And in this data structure, 1 point will put into multiple buckets, and we only repeat 1 time. In the query phase, we pick a point Q prime from Q, and also query multiple buckets. And with the same performance as the standard LSH, there is a 1 bucket such that P prime and Q prime, if they are close, they will meet each other. However, there's still an issue that the far point, this black point, also fall into this bucket. And we use asymmetric locality-sensitive hashing to get rid of this problem. For the asymmetric locality-sensitive hashing, we make it to an extreme, such that in the pre-processing phase, a point can be put into so many buckets, which is n to the 1 over epsilon squared. And meanwhile, the query point, because we do so much effort in the pre-processing phase, so in the query phase, the query point can just need to query one bucket. And we can guarantee that in this one bucket, we already have 0.5 probability that a closed pair P and Q will collide in this bucket. And on the other hand, for any far point from Q, the probability they collide is at the most 0.1 over n. Hence, we can use the union bound to conclude that for any fixed point Q and a fixed point P, if they are close, they will have larger than 0.4 probability that they collide, and also Q doesn't collide with any far point. I should emphasize that P might be Q might collide with the other close point in the set Q. However, because we are doing the directed spanner, Q will never have a chance to arrive Q prime. So we are safe. And to deal with this issue of creating too many copies, we can split the set P into many sets of small size, which is only n to the epsilon squared over 2. And for each set, we prepare the data structure. So overall, in each set, we only cost n to the root n. We only copy root n times, which is smaller than n. To conclude, we prove that first of all, to achieve 1 plus epsilon approximation, we need a non-matrix standard point. And using the non-matrix standard point, we are able to construct directed spanner of sub-quadratic number of edges, also the undirected spanner with slightly worse performance. And noted that the construction time is also in time linear in the size of the spanner, which is also sub-quadratic. We have a few questions to ask. Is there any smaller spanners in Hamming spaces or the Euclidean spaces? It seems that n to the 2 minus epsilon is possible because all the applications of the locality sensitive hashing has only 1 epsilon instead of 2 epsilons. And also, do we have lower bounds to rule out even slightly larger than linear size when non-matrix standard points are allowed? It seems that non-matrix standard points are powerful, but it's also hard to analyze. And do we have more applications of our spanner construction? Thank you for listening to my talk.